Okay, so right, so good morning, everybody. I'm Simon Blackburn, chairing the session. So I'd like to introduce Colva Dougal, who's Professor of Pure Mathematics at St Andrews. She's known for her work in group theory and in computer algebra. So in particular, she's classification of maximal subgroups of classical groups of low dimension over finite fields. So she had a project on this that, along with Derek Holt and John Bray, which led to a book on the classifying groups with a dimension less than or equal to 12. She's also known for her work in constraint satisfaction and symmetry breaking, using techniques from group theory, and on the classification of primitive permutation groups of low degree as well. So I think everybody's up to, I think, about 4,095 at the moment. And she's going to talk on base sizes. Oh, and also I should say, for combinatorial people, she was the organizer of the fantastic conference at St Andrews about 10 years ago. And you'll remember, at least, if nothing else, you'll remember the fire at some point that she coped admirably with as organizer. So yeah, so a long-term friend of the BCC as well as the computational group theory community. And so she's going to talk on base sizes and relational complexity of finite permutation groups. So yeah, please go ahead.
Thank you, Simon. Thanks for the lovely introduction, and thanks to the organisers for inviting me. I'm really honoured to be speaking here. It never occurred to me 12 years ago when I was organising that one time I would come back as a plenary speaker. So yeah, that's a lovely feeling. So what I'm going to do in this talk is start out giving a kind of survey of some of the stuff that Simon just mentioned. So bring you up to date on where we're up to with some projects concerning maximal subgroups and primitive groups. And then, since this is a combinatorics conference, not a group theory conference, what I want to do is talk about some things we can do with that information that I think are hopefully of particular interest to combinatorialists. So I'm not expecting the audience here wants to classify maximal subgroups, but what can you do with the work that the group theorists have done? So in my survey article, I talked about 3 main applications. I'm just going to focus on one of them here, partly because it's the one that's caught my attention most in the past year, and partly because another one of them is going to be, I think, excellently covered in Martin Burrow's talk on Friday, which I'm really looking forward to. So let me start by telling you about the classification of finite simple groups. So here's a nice clean statement of the classification. So if we want to know what a finite simple group is, then let's call it T. Then it has to be one of the following families. So it could be cyclic of prime order. So think of the integers 0 up to p minus 1 under addition. It can be an alternating group on n points where n is at least 5 if we want the thing to be simple. It can be a group of Lie type. I'll talk a little bit more about that in a bit, but there's 2 main sorts of that. They could be a classical group or an exceptional group. So that's really where the majority of the examples lie. So all of these families so far are infinite, but in some sense the groups of Lie type are the most infinite. Or finally, there's magically just 26 leftovers that don't fit into those 3 infinite families. So we've had this classification for a while now, and that's great. And I've just told you in 4 lines what the finite simple groups are. But all I've really done is named them. And a name is wonderful, and it's good to know that we have a complete list of names, but really it doesn't tell you all that much about what the things are. So what are the main things we might want to know about this list of groups? So the 2 obvious things that come to mind for me are, what's their internal structure? So that could mean structure of elements, so conjugacy classes, but I've always been somewhat more interested in subgroup structure, so what groups sit inside these. And the obvious first place to start if you want to know what groups sit inside them is to want to know what the maximal subgroups are. So what are the largest subgroups inside each of these groups? So I'm going to write max G for the maximal subgroups of a group G, and for those that care, that will be up to conjugacy in G. So I'll be keeping conjugacy class representatives at each point. Well, that's a group theorist way of thinking about something we might want to know inside them. Equivalent statement is to say, how can I represent these groups? How can I think of these groups as groups of permutations? How can I think of these groups as groups of matrices? Or More combinatorially again, what kind of objects have these things as groups of automorphisms? So rather than just having a list of names, could I instead have a list of combinatorial structures associated with all of the finite simple groups? That would be a lovely way to understand these things. So I'm going to talk about both of these questions along the way, but it turns out, although I phrased all this in terms of the finite simple groups, that's not quite enough. So a group G is almost simple, and this came up in Cheryl's talk yesterday, if there exists some non-abelian simple group T that's a normal subgroup of G. So I can see T sitting inside G as a chunky normal subgroup, and actually T is almost all of G. So a non-abelian simple group, you can make it act on itself by conjugation, so you can identify it with some of its own automorphisms, and then that means it sits inside its own automorphism group because none of the elements of T centralize all of T. And so G is sitting somewhere between T and ought T. And it's non-obvious, depends on the classification theorem, that actually the gap between T and ought T is quite small. So there's not very many possibilities there between T and ought T. So we've got this smallish number of possible ways of extending T to give us something called an almost simple group. And our right soc G is called the socle of G for that big chunky simple group sitting inside G. Well, why almost simple? Well, it turns out if you want to then put the bits back together again, so not just talk about simple groups, but to talk about almost simple, so all groups, it's not enough to know about the simple groups alone. So there's a pair of results due to Kovac and Ashbacher and Scott from ages ago, and I meant to check the date and I forgot, sorry, which says if we know the maximal subgroups of all of the almost simple groups, then it's possible to put that information together to work out the maximal subgroups of every finite group H. Now, I phrased this quite vaguely. You can do this in a computational way. It does involve some problems with cohomology, which is really not my bag, so we're not going to talk very much about that. But in theory, if I knew the full list of all of the maximal subgroups of all of the almost simple groups, I could write down for every finite group H its maximal subgroups. So that's the goal. And when I was first asked to give this BCC talk, once I got over the horror of not feeling like I was up for it, I started thinking about previous BCCs, and I remembered Oliver King's BCC thing from 2005, where he talked about Ashbacher's theorem. And I thought, well, let's bring this up to date. Let's talk about maximal subgroups, giving a nod to talks that have gone before. So I'm not going to go through all of these. Suffice to say, the maximal subgroups of a cyclic group of prime order are quite easy to classify. There's only the identity there, thanks to Lagrange's theorem. And the exceptional groups, there's been a lovely announcement by David Craven recently. There's a preprint. The maximal subgroups of the almost simple exceptional groups are now known. I'm not going to say any more about them. They're done, finished, complete. And for the sporadic groups, with the possible exception of two almost simple subgroups of the monster where we don't know if they exist or not, otherwise the sporadics are done. So in some sense, CP, exceptional and sporadics can be deemed to be complete. And if you need to know something about one of those, it's there, it's in the literature pretty much. So I'm going to talk about the remaining two. So the alternating groups and the classical groups. So to talk about the alternating groups, I need to give you some permutation group basics. So I'm not assuming everyone's a group theorist here. So I'm going to write Sn. So sim omega will be the full symmetric group on a set omega. For Sn, I'm going to mean specifically the points 1 up to n. And let me slowly talk through how we might think about classifying the almost simple groups with socle an. So if n's not equal to 6, that means that the group is either an or Sn. So I'll write x for Sn or an, and we'd like to know about the maximal subgroups of x. And n's at least 5, because I want it to be almost simple. So the orbit of a point in omega, so I've got some group acting on omega. So I'm going to stick with G being a subgroup of sim omega, is all of the places I can map alpha to under G. And you'll see here, I'm going to write my group action as conjugation. So everything I can send alpha to is the orbit of alpha. And then I say that a group G contained in sim omega is transitive if G's only got one orbit. So I can take my favorite point, say point 1, and send it to everywhere else. So the obvious first split we might have is, are you transitive or are you not transitive? So let's think about subgroups of Sn or An. Well, if I fix some k points, then I can write down a maximal subgroup of Sn that acts as Sk on those k points and acts as Sn minus k on the other k points. Well, the alternating group can send any k points to any other. That's an easy exercise. Just write down however you like and then make it an even permutation. So I only get one conjugacy class of subgroups for each value of k. So if k is not equal to n over 2, then I get a unique group up to conjugacy that is either Sk cross Sn minus k if I'm in the symmetric group, or half that if I'm in the alternating group. And it's a very easy exercise to show that in fact you get a maximal subgroup of Sn there. So if you pick any permutation that's not in Sk cross n minus k and throw it in, and then take all of Sk cross Sn minus k as well, then you can write down any permutation. And it's not much harder to do that with the alternating groups. So there's our first family of maximal subgroups. And I've deliberately omitted k being n over 2 because if you think about it, there's an extra thing you can do there. Right, so great. That's actually quite a lot of the maximal subgroups we've just listed there for most values of n. So if we take a subset delta of omega, then we say that that's a block for my permutation group G, my subgroup of sim omega. If for every group element in G, when I look at what happens if I hit every point in delta with G, so by delta to the G, I mean act on the whole set, and look to see how many of those images are in the set delta, well, either none of them are, I've moved delta completely outside itself, or all of them are. So I've either sent delta completely back to itself, or I've sent it completely outside itself. Such a subset is called a block. Now, we've always got some trivial ones of those. So if delta's got size 1, then that has to be true because there's nothing else the intersection could be. And if delta's the whole of omega, then that's always true because there's nothing else it could be. So if G is transitive and delta's a block, well, it's a comparatively easy exercise to show. If I look at all of the images of delta under G, well, they all have to intersect trivially. So the set of images partitions up omega. And so you can think of this block as having yielded a really nice partition on the set into parts of equal size. So then if delta's got size k and the number of points I'm acting on is a multiple of k, then the stabilizer of the partition in X, which is An or Sn, is this wreath product. Don't worry too much. I mean, that's everything you can do while stabilizing the partition. So if you prefer to think about partitions, it's all of the symmetries of that partition. I can move the parts around and I can do anything I want to inside the part. Now, An is transitive on these partitions. So we're only going to get one conjugacy class of groups corresponding to partitions. So I don't need to care about exactly what delta we're picking. I just need to say, well, K and M. And it's a little bit of work, but not too much work to show that with actually just one exception, you always get a maximal subgroup like that. So the one exception is inside the alternating group on 8 points. It's okay in S8, but it's not okay in A8. That's an extra thing you can do. All right, so that's more maximal subgroups. So we've got these transitive ones, and then we've got these wreath products, so these stabilizers of partitions. So I'll say that a group G is primitive if it's transitive, so we send any point to any other, and there's no proper non-trivial blocks. So all blocks have got size 1 or the whole thing. Well, I've just talked about all of the ways in which I could have an intransitive maximal subgroup and all the ways in which I could have a stabilizer partition. So the remaining ones have to be primitive. And so all of our remaining maximal subgroups are primitive. And the primitive groups are described by the Onan-Scott theorem. I'm not going to tell you the Onan-Scott theorem because it would take up too much of the talk, but I'm just going to say it divides them up into 5 classes. And one of the classes, unfortunately, is almost simple groups. So I'm going through talking about how we classify maximal subgroups of almost simple groups. And unfortunately, I have hit a class of maximal subgroups which is itself the almost simple groups, which sounds a bit recursive, but fortunately these things have to be smaller. So if we're trying to classify maximal subgroups of almost simple groups, we can bootstrap our way through here. So let me talk a bit now about primitive groups. So there's a really important paper by Martin Liebeck, Cheryl Prager and Jan Saxel from 1987, where they completely classify the not almost simple maximal subgroups of the alternating and symmetric groups for all n. So if you want to know about the ones which aren't almost simple, look in that paper. It's big, lots and lots of tables, but the full answer is there. So that means that to understand the maximal subgroups of AN and SN, what do we need to know? We just need to know the almost simple ones. But actually, in general, we're quite interested in knowing all of the primitive groups. So Simon kindly trailed this before, but one of the first things I did after my PhD was to get interested in classifications of primitive groups. And the furthest published point at the moment is by my PhD student, Hannah Coates, together with Martin Quick at St Andrews in 2011. We classified the primitive groups on up to 4,095 points. Derek Holt's PhD student, Ben Stratford, has pushed this a lot further, like really a lot further. I think the non-affine one's up to degree 1 million, but it's not yet published. So huge leaps and bounds are going on with those numbers. So yeah, if you need to know for a particular value of n what the maximal subgroups are, you can work it out from these lists of primitive groups, in particular using further results of Liebeck, Prager and Saxel. And if you want to know a particular primitive group, they're in GAP, they're in Magma. You can play with them looking for examples. Right, I'll say that a primitive group, G, and the reason for this name will become apparent in a bit, but it's going to be called large base. If up to permutation isomorphism, so don't worry too much about what that is. It's a strong notion of equality. One of two things happens. So either the set omega is all of the m subsets of 1 up to k, and G is AK or SK acting on these m subsets. So these came up yesterday in Cheryl's talk. Actually, you can think of these as these Johnson graphs, and what we've got here is the automorphism group of a Johnson graph. But if you'd rather think about it as literally just acting on subsets, then of course you can think about it that way too. So that's one possibility. We're alternating or symmetric, and we're acting on the set of all subsets of the natural set of points. The next possibility is we take that on steroids, and we take all L tuples of subsets of 1 up to k. And now what we're allowed to do is act independently on each entry of our L tuple, and also permute the L tuples around. So that means in group theory language, G is a product action group, and it contains the whole of AK to the L. So I can definitely do each of AK on M tuples to each coordinate, but I can also permute them around and do more stuff as well. So these are called the large base groups. And Marotti in 2002, and I noticed this theorem is also in Martin Crowe's paper, showed that if G is a subgroup of Sn and is primitive, so what I'm wanting to do in the next little bit is talk to you about what can we do where we don't have these full classifications. So here's one thing we can do for the values of n where we don't know the maximal subgroups. Marotti showed if G is primitive and is a subgroup of Sn, then either G is large base, so I've just given you quite a precise description there of what G is, you can work directly with that description, or it's a mature group, MN, so natural representation on n points, or it's small. In particular, it's got size at most n to the 1 plus log n. So that tells you that if you want a very coarse classification of primitive groups, you've got these mature groups, which we all know and love. You've got these large base groups where we've got a very precise description of the action, or it's quite small, and maybe you can use the fact that it's small to come up with some arguments to do what you're wanting. Now, an even stronger version of that, but just applying to some of the groups, so these come kind of looking backwards, if G is almost simple and primitive, so I put the extra restriction now that we're only talking about the almost simple groups, then we can say even more. So let T be the socle of G, so that's the simple group sitting inside it. Then either G is large base, so that's these Johnson graph examples acting on subsets, or we're alternating or symmetric, and now rather than acting on subsets, we're acting on the set of all partitions of 1 up to m. So I've talked you through that action on partitions already. Or It's a classical group, and I'll talk a bit more about this but on the next slide, but each classical group has a natural vector space it wants to act on, and so we're acting on subspaces or just possibly pairs of subspaces. Or, so we're going to make a more precise statement so we have more options, sadly. Or, here's the final one, it's really small. It's got a size at most n to the 9. So we're not talking like n to the log n here, we're genuinely n to the 9. It's teeny, teeny, tiny. So for lots and lots of applications, again, first 3 cases, we have quite a lot of information about the action, not quite as much as we did for Attila Marotti's thing, but we've got a tighter bound at the end of it, or it's really, really tiny. So let's switch now. I just said I was going to talk a little bit more about classical groups, so let me talk a bit more about classical groups. I don't want to get into lots of technical details about the classical groups, so let me just say that they're naturally represented as, to be precise, quotients by scalars, but subgroups of the general linear group. Think of them as groups of matrices over finite fields. Q is a prime power, U is either 1 or 2. It's 2 for the unitary groups and 1 for everything else. Quotients by scalars if you want the simple group, or alternatively take your matrix group and make it act on projective space and the scalars will disappear and the image of that action is exactly going to give you the simple bit. So they each come with some kind of natural module, V, I'll call it, which is a vector space over a finite field. And if we're talking about some of the classical groups, then we don't put a form on, or you put the form that's identically 0 everywhere on. Otherwise, we put a classical form on. So the maximal subgroups of the classical groups are divided up into 9 classes by Ashbacher's theorem, which I absolutely am not going to tell you, but there are these 9 classes. And just like me not telling you the Onan-Scott theorem, most of the classes come with quite a precise structure and action. And then there's one class, which is the almost simple groups. So we keep having this problem that we get these lovely classifications, but one of them is all the stuff we've been trying to classify in the first place. But of course, it's now a proper subgroup of the stuff we were trying to classify at this point. And so once again, one can hope to bootstrap. The other classes, so the other 8 of them in Ashbacher's theorem, are all called geometric. So we can hope to make some statements about geometric subgroups versus almost simple maximal subgroups. So Clive and Liebeck in 1990, so now if G is an almost simple classical group, for dimension at least 13, so a natural module of dimension at least 13, we're talking matrices of size at least 13 by 13, then we know all of the geometric maximal subgroups of G. All of them. So these 8 classes for Ashbacher's theorem that I've not told you about, we know the maximal subgroups in each of those 8 classes. We know when they're contained inside an almost simple subgroup, even though we don't necessarily know what the almost simple subgroups are, but we do know completely when the geometric ones are maximal. And then, so some of this was done by me with John Bray and Derek Holt, and then the next bit was done by my PhD student, Anna Schroeder, and then the last bit was done by Derek's student, Daniel Rogers. So let G be an almost simple classical group in dimension of 17. Then we know the maximal subgroups of G if the dimensions are most 15. So we know completely. So Derek and John and I did it up to dimension 12, and then my student Anna did 13, 14, and 15. And then we also know the maximal subgroups of G with just a couple of tiny exceptions. So for dimensions 16 or 17, we're all good unless G is orthogonal and not simple. So there's a couple of almost simple orthogonal cases where we hit a Galois group problem and we can't quite describe what's happening where. So roughly speaking, if the classical groups you're wanting to look at aren't too big, then we do know the maximal subgroups, and there's tables and you can look them up. Or it's not in GAP, unfortunately, but it's in Magma. There's a function classical maximals, which will just write them down for you and you can play with them. So if you're trying to make nice examples, for dimensions not too big, you can have all of them and we can promise that that's all. What can we say about bigger things than that? Well, once again, it's the theorem of Martin Liebeck, this time from 1985, which says that if G is an almost simple classical group, and H is a maximal subgroup of G that's not geometric, so it's this class containing almost simple groups. I don't want to just call it almost simple because some geometric subgroups are almost simple. There's lots of extra conditions going on there, but it's a non-geometric maximal subgroup of G. then either H is alternating or symmetric, and we know M is either D+1 or D+2. So this is essentially represented as permutation matrices and then take some natural quotients to make the thing irreducible. Or H is tiny. So Q to the 3D. So this is field size to the 3D, basically. So either it's alternating or symmetric, we know exactly what the action is, or it's really quite small. If you think about the general linear group as having size roughly Q to the U times D squared, so we've got D squared in the exponent, this is much, 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 much smaller than that. Vanishingly small as the dimension grows. So again, for smallish ones, we know what they are. For biggish ones, we know that the known unknowns are not very big, to quote somebody else. Right, so that's where we're up to at the moment with the classifications. We know a huge amount now. I think for the average user of groups, we probably know as much as you might want to know at this point, unless you're particularly greedy. So now let's look at some games we can play with these. So by G, it's still going to be a subgroup of sim omega with a whole bunch of alphas below there. I mean the stabilizer of each of those points. So the set, which turns out to be a subgroup of elements of G that map each alpha I to itself. So the pointwise stabilizer. All right, then a base for G is a sequence of elements of omega. So I'm going to care what order they come in. So it's a sequence for me. I'll put a little line under the beta to indicate that I care about the ordering, such that the pointwise stabilizer of those elements, so just to remind you, the round brackets thing means I'm pointwise stabilizing those elements, is the identity. So there's two ways you can think about this. You can either think of it as I first of all find the subgroup of everything that fixes the first point, and then inside that stabilize the next point, and then inside that stabilize the next point. Or you can think of it as I take the stabilizer of the first, the stabilizer of the second, and so on, and then I intersect all of them. Different people prefer to think about it different ways, and for different purposes, it's easier or harder to think of it either way around. Why are these important? Well, from a computational group theorist point of view, this is why they're important. Other people may have other motivations. So let's imagine I've got two group elements and I've got some base here. And let's imagine that G and H send each of the elements of the base to the same place. So alpha I to the G is the same as alpha I to the H for 1 up to I up to K. Well, what's that equivalent to? That happens if and only if, well, undergraduate rearrangement. That's the same as alpha I to the GH inverse is fixed by GH inverse for all I. And then let's look at our definition of a base. Well, the only thing which fixes everything is the identity. So that happens if and only if I just picked the same element twice. So the base point images uniquely determine the group element. So from a computational point of view, this means that rather than storing group elements as a whole permutation, I can store them as just a sequence of base images. That's a much smaller amount of data. And in general, this means that somehow the action of the whole group is being determined by this small subset of what it's doing. They're really, really fundamental to computing with permutation groups. I could talk about this for ages, but let me just give you one reason why. So suppose I've got some subgroup G and Sn, and then somebody gives me a permutation and says, is this in G or not? Well, if I know a base of size B, say, then I can decide whether or not the permutation you've just given me is in G with an algorithm of complexity big O of n times B. So the B is really, really important in how hard is it to find out whether or not this thing's in a group element. Right, let me just give you a few more definitions here. So I'm going to write B of G, or if I need to specify the set, B of G omega for the size of the smallest base. So what's the smallest number of points whose images determine the group element? Then I'll say that a sequence alpha 1 up to alpha k is irredundant if each time I stabilize one more point, so I've stabilized up to alpha I, stabilize one more point, I drop. So each time the stabilizer is properly smaller than it was before. So nothing is already stabilized. I'm not wasting points. And I'll write I of G for the size of the largest irredundant base. So the smallest irredundant base is little b of G. I of G is the largest irredundant base. So I've done what looks like a sensible thing. My point stabilizers have got smaller as I've worked my way down, but what's the longest that could have taken me? Then we'll say that this is a less common definition, but it's going to turn out to be useful later. A subset delta of omega is called independent if, whenever I stabilize pointwise, any subset of delta, so gamma contained in delta, proper subset, I get a different subgroup. So I get something bigger. So if I fail to stabilize all the points in delta, then my group grows. And we'll write H of G for the size of the largest independent set. That's called height. Then there's a nice elementary argument. So the base size, a minimal base, is certainly independent, because if I fail to stabilize a point in a minimal base, I no longer have the identity. And any independent set, well, in particular, as I work my way down through the independent set, my point stabilizers have to drop each time. Otherwise, I wouldn't have an independent set. So that's certainly irredundant. So little b of G is less than or equal to H of G is less than or equal to I of G is elementary. Let me give a couple of other things about base size. So pulling over to computational things here. So Charles Sims is really the person that made us all realize how important bases are. He proved back in 1970 that you can compute an irredundant base in polynomial time. So I can definitely, on input, some collection of permutations, I can compute an irredundant base in poly time. And then there's a lovely short paper by Blaha from 1992, where he showed that computing a base of minimal size is NP hard. So even verifying that the one you've got is minimal size is not polynomial. Deciding if there exists a base of size at most a given size is NP complete. So these are hard problems. Conversely, you can compute a base of size big O of the minimal base size times log n in poly time. So there's an obvious greedy algorithm for computing a base, which is stabilize a point, pick something in the biggest orbit that's left, stabilize that point, pick something in the biggest orbit that's left, stabilize that point. That will give you one, he proves, of size minimal times log n. And you can do that in poly time because I just told you how to do it in poly time. Right. Let's press on. Let me give you some examples. So that was an awful lot of definitions. So let me give you some examples. So the symmetric group. If I want to stabilize points in Sn, well, I want to get down to the identity. Pick a point, stabilize it. Pick another point, stabilize it. Pick another point, stabilize it. I don't care what point you picked. I'm going to have to go all the way down through n-1 of them until there's only 1 point left. Otherwise, I could still swap to. So for the symmetric group, all irredundant bases have size n-1, and they're the same as the minimal bases, and any n-1 tuple will do. Really strong, obvious condition there. For the alternating groups, something similar happens. If I'm at n-3, I've still got a 3 cycle. Pick one more, and I'm finally done because I'm not allowed the involution. So any set of size n-2 will do. And again, we get equality here. Those are really, really big numbers. Not nice for the point of view of computational complexity, but that's okay because AN and SN are special. And we can write special purpose algorithms for computing inside the whole of AN and SN. Let's look at a really small example. So let's have G be cyclic on n points. Well, here, conversely, if I stabilize any 1 point, I get down to the identity. And again, the base size, the minimal base size and the largest irredundant base size coincide in just 1. So just to show you that this doesn't always happen, oh no, I don't want to do that yet, that's next slide. Rather than just flailing around doing examples, let me prove a little tiny lemma. So if H is a subgroup of G and curly B is a K tuple of points, well, the intersection of all of those point stabilizers in H is certainly a subgroup of the intersection of all of the point stabilizers of G, because H is contained inside G. So that means in particular, the minimal base size of H is at most the minimal base size of G, because if I get down to the identity with G, then I must have got down to the identity with H. And conversely, turning it the other way around, the irredundant base size of H is at most the irredundant base size of G, because if I'm dropping each time inside H, then I'm certainly dropping each time inside G, but I might have some points left over by the time I've finished up using H. So that means that both of these invariants and the height as well are nice with respect to subgroups, and so it's okay to start talking in the first instance about maximal subgroups of Sn and An if we want to get a handle on these, and they'll give us some sense of upper bounds on these different kinds of base size. So let me do that. So firstly, let's look at these stabilizers of k points. Well, if I want to find a base for sk cross Sn minus k, this must be like the 6th time this group has come up now, well, I have to stabilize all but one of the first k points and all but one of the second k points, and so it's n minus 2, and same for the irredundant. Okay, well, that was our first family of maximal subgroups of Sn. Our next family was the stabilizers of partitions. Well, if I want to stabilize, if I want to get down to the identity in the stabilizer of a partition, well, again, I need to stabilize all but one of the points in a block, and then the last point in the block is fixed, and then all but one of the points in the next block, and then the last point is fixed. So the minimal base size of G, all but one of the points in each block, and I need to do that for every single block, sadly, so it's still pretty big, n minus k. And that's the same as the irredundant base size. So these are still big, 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 big numbers. Sadly, I'm looking for nice small base sizes. These are all huge. And also everything I've shown you so far has minimal base size the same as the irredundant base size. So why am I bothering with all of these different definitions? I thought I'd pick a cute example from a PhD thesis I examined last year. So let G be PGL acting naturally on one-dimensional subspaces of FQ to the M. Well, let's assume Q is at least 3. Then there's an obvious minimal base size for G, which is that you take a basis and then you take something with full support. So a vector that's non-zero in every coordinate, that's a frame. And once you've stabilized a frame, then you're down to the just the scalars. Okay, so that's minimal. But Bianca came up with this lovely construction where if instead you take a full basis, so V1 up to Vn, that's my standard basis, say, and then I take these sums, so V1 plus V2 plus V3, V1 plus V2 plus V4, all the way up to V1 plus V2 plus Vn, well, that turns out to be an independent set. So, and in fact, it turns out to be an irredundant base. So get down to the identity with that, but you get down really, really slowly. And if you miss out any one of those points, you're not yet down to the scalars. And so here is a nice example of where the irredundant base size is 2n minus 2, but the minimal base size is n plus 1. It's a really pretty construction, that one. All right, so those numbers were, and I just used n for both, I do apologize. D is quite small relative to q to the d minus 1, so that was a much smaller base. So let me now focus on base sizes for primitive groups. And let's think first of all about these large base primitive groups. So there's a theorem due to Halaschi in 2012, which says that if G is SK acting in a large base fashion, then the minimal base size of G is big. This is like a square root of the value of n. So the size of n is k choose m, and then this is looking like is O of k. So we're looking like a root of n. And if m is no more than the square root of k, then this bound is actually an equality. Okay, so these are some of the large base groups, and that's because they have large bases. And I'm not going to go through the other kinds of large base groups, but they also have large bases. So there's a lovely theorem due to Martin Liebeck, which says that if G is primitive and not large base, all the examples I've given you so far for like the intransitive groups and the imprimitive groups, they had bases of order big O of n. I mean, they're quite close to n. But if we're primitive and not large base, then boom, the minimal base size drops down to 9 log n. Logarithmic, not linear, log. Which has a corollary from Blaha's result that if G is not large base, then I can construct a base of size big O of log n in poly time. So it gives me a polynomial time construction of a pretty small base. So let me tell you about a couple of conjectures which really dominated this field for many years. So let G be almost simple with so-called T, then a transitive action is called standard if up to equivalence of actions, don't worry, strong notion of equality, either T is AK and once again, these large base orbits of subsets or partitions. So the partitions pop up again here. So our two examples that keep appearing, acting on subsets or partitions. Or G is a classical group in a subspace action. Roughly speaking, that means acting on subspaces. There's a couple of other things that can happen. Then Peter Cameron and Bill Cantor conjectured in 1993 a really startling thing, that there exists an absolute constant C, such that if G is almost simple and is not one of these standard things, so not subsets, not partitions, and not acting on subspaces, then the base size is bounded by this absolute constant C, which sounds like it shouldn't be true, but is. So it's proved in 1999 that it's true, but initially we didn't have the actual value of C, and then Tim Burness and collaborators over quite a few papers eventually showed that in fact that constant C is 7. So to describe the action of the almost simple group, 7 points suffice. Only one example where you attain the number 7, match your group, 24 points. So that's our pretty example. There's literally just the one. So its natural action on 24 points is big, and you need to stabilize 7 of those points to get down to the identity. Infinitely many examples with base size 6. Okay, so this is really, really startling and beautiful. So for almost all of the primitive groups, apart from these ones where we understand what they are, telling you the images of 6 points suffices to tell you what group element I'm talking about. I don't need to tell you what it's doing to 10 million points. I can tell you what it's doing to 6. Right, I'm actually going to skip this next slide because I'm going slow. So let me give you some new results on minimal base size. So I just showed you Liebeck's result that if G is primitive and not large base, then the base size of G is at most 9 log n. I got interested in this for computational considerations and just noticed that there wasn't any proof that that 9 was sharp. And I've also just told you that the base size of M24 is 7. It's easy to see that the minimal base size of AGLD2, so let's take the vector space, F2 to the D, and then put GLD2 acting on it as well. Well, you stabilize 1 point and then you stabilize a full basis. So stabilize the 0 vector and then stabilize a basis and you get down to D plus 1. And that's precisely log n plus 1. So here are our 3 things we know. We know it's at most log n. We've got an example where it's 7, which is actually quite a large proportion of 24. And we've got an example that hits log n plus 1. Well, with she's a postdoc now, Maria Pia Moscatello. We proved last year, it just got accepted a few days ago, that if G is primitive and not large base, so again, we're excluding the large base groups, if G is not the matcher group on 24 points, then in fact, never mind the 9, we can take it as 1 times log n plus 1, provided that you round up. You must round up. And in fact, we classify all of the groups G where the rounding up is necessary. So essentially it's just the matcher groups and then some particular examples of symplectic groups acting on orthogonal forms, which also popped up in Cheryl's talk yesterday. It'd be quite nice to know which ones hit exactly this bound. They're all subgroups of AGLD2, but we decided it was going to make our paper longer than we wanted to classify them, but it'd be quite nice to know exactly which ones need that. So this is minimal base size. There's also been some new stuff out recently on H and I. So let G be primitive and not large base. Then this is what got me interested in H and I actually, was Bianca's thesis, which has now been turned into a paper by her and Nick Gill and Pablo Spiga. They showed that this other invariant I talked about, the maximal size of an independent set, is at most 9 log n. And Bianca's thesis was lovely. The key observation that makes this tractable is that I talked about the standard actions of the almost simple groups. They have the minimal base size of G being at most 7. Well, that means that the size of G is at most 7 to the n, because each time I stabilize a point, I drop by at most n points. And so the independent maximal size of an independent base is at most minimal base times log n, which is at most 7 log n. So that meant that Bianca didn't have to deal with the non-standard, sorry, that should say non-standard, with the non-standard actions of the almost simple groups. She only had to deal with the ones where we know what the actions are. And so she was able to go through the Onan-Scott theorem, lovely thesis, and do all of that. So it suffices to analyze the known primitive groups. So I looked at this and it was great. And they had a conjecture. So this is about this slightly strange invariant at the height, that there should exist a constant C such that the irredundant base size, I've just shown you a proof that it's at most log n times log n for some constant C, but that actually we should be able to get at most C log n. And that's what my very bright PhD student Veronica Kelsey's just done. We've shown that in fact the irredundant base size of a non-large base primitive group is at most 5 log n. So we actually beat the 9 that they had before. So we've pushed the height down along the way. We got all the way down to 5, which has a really quite nice corollary. It means that in polynomial time, you can compute a base for a non-large base primitive group of size at most log n. So we're no longer stuck with log n, log n for the base size that you can get to in poly time. You can actually get to one of size 5 log n now in poly time, just by the obvious algorithm, because if it's irredundant, it has to stop there. Right, I promised a link to model theory, so I just raced through a couple of slides so I would have time to do this end bit. So let me tell you a little bit now about this link to model theory. So a relational structure, curly R, is a set omega and a bunch of relations, R1 up to Rk. So omega is going to be a set, each Ri is a relation on omega, and it's going to have some arity. So could be binary, so just relating pairs of points of omega, but it could be bigger, and I'll write Li for the arity. And I want each one to have arity at least 2. The arity L of R is the maximum of all of these Li's. So find the biggest one. They don't all have to have the same arity. That's also sometimes called the type of R. I seem to see both names in papers and I wasn't sure which was the more common, but I've written arity because I thought it was easier to remember. So for example, if I have a single relation and it's got arity 2, then what am I talking about? I'm talking about digraphs. So hopefully lots of you are familiar with this language of relational structures, but if not, I mean, we're all used to binary relations. We're less used to ternary and higher relations, but there you go. So an isomorphism from R to some other relational structure S is kind of what it has to be, but quite a strong version of what it has to be. So it obviously has to be a bijection from omega to gamma. Wouldn't make sense to call it an isomorphism otherwise. And then the strong condition is that I want it to map each relation to the corresponding one in the right order. So it's not allowed to somehow jumble them around. It has to send phi of Ri to Ti for all I. So first relation goes to first relation, second relation goes to second relation. I'll say that an induced substructure on some subset of omega is what it has to be. So you drop down to the set being delta, and then you take the intersection of your relation with that set. So the things that are just on that set. So R1 meet delta to the L1 because that's the arity of R1, all the way through to Rk, meet delta to the Rk. So for example, if R was a digraph, then an induced substructure would just be an induced digraph. Take the fully induced digraph there. Then we say that a relational structure is homogeneous if whenever I pick 2 subsets of omega and I take all of the isomorphisms, any isomorphism between the induced substructure on gamma and the induced substructure on delta, then there's an automorphism of R, so an isomorphism from R to itself, whose restriction to gamma is exactly this map phi. So any local symmetry extends to a global symmetry. So plenty of people have looked at homogeneous graphs and digraphs. So Gardner classified the homogeneous graphs. In geometry, homogeneity winds up being Witt's lemma, which says that any isomorphism between substructures of a space with a classical form extends to an isometry of the whole space. Homogeneity is a beautiful, beautiful thing. And so we're going to be interested in what can you say about homogeneous relational structures. Okay, well, let G be, and for convenience on this slide, I'm just going to talk about non-trivial groups G. Then the relational complexity of G is defined to be the smallest L such that there's a homogeneous R of arity L, so some homogeneous relational structure whose automorphism group is G. So suppose I want to find a combinatorial object where G is the automorphism group, and I'd like it to be homogeneous. What's the smallest arity I can do it with? There's a construction that says you could always do it on at most omega points. You throw down the orbits of G on everything, and the orbits of G on everything winds up being homogeneous. It's not very interesting. Okay, well, here's another way of thinking about relational complexity, because I don't know about you, but that's kind of motivating, but it doesn't help me get my hands on it. So let I and J be two M tuples, then I say that I and J are K subtuple complete. If whenever I pick K coordinates, there exists a group element, G, sitting inside sim omega, which maps those entries of I to the corresponding entries of J. So whenever I pick K coordinates, I can send the I thing to the J thing. Let's just see that this always has to be at least 2. So I've assumed G is non-trivial for this slide. So let beta be something that I can map alpha to that's not alpha. And let I just look like alpha alpha. So there's no requirement for these tuples to be distinct. And let J look like alpha beta. Well, I can send alpha to alpha and alpha to beta. So that tells me that I is one subtuple equivalent to J. But I can't send the whole pair over. Okay, so I can send individual things over here, but I can't send the whole pair over. Okay, well, Churlin, Martin, and Saraceno in '96 showed that the relational complexity of G, this thing about the existence of a homogeneous relational structure, where I don't know necessarily how to find such a thing, is equal to the minimal value of K, such that whenever I take M greater than or equals K, and whenever I take 2 M tuples of elements of omega, if the M tuples are K subtuple complete, then in fact they're M subtuple complete. So if I can map any K over, every K over, then I can map the whole lot over. This is still a bit of a mouthful, but less of one. Let me give you a couple of quick examples. So if G is cyclic, 1 up to N contained in Sn, then suppose I take 2 M tuples for some M, and I can send the points over 1 by 1. Each individual point maps over, then that doesn't tell me very much because there's this obstruction. Okay, imagine instead I can send the points over 2 by 2. I can send any pair of points over. Well, in G, there's only one group element, which sends any point to any other point because it's cyclic. So if I can send every pair of points over, I can send all the points over. So the relational complexity is actually equal to 2. Relational complexity of Sn, well, provided I can send every pair of points over, that means I don't have anything that looks like this, where they're equal in one of them and not equal to the other. So again, the relational complexity of Sn is 2. With a bit more work, you can show, however, that the relational complexity of An is huge. It's n-1. So this property is not nice with respect to subgroups. It's quite wild with respect to taking subgroups in some ways. Let me just give you the definition here. So a permutation group G is binary if it has relational complexity 2. So what I've shown you here is, in fact, this argument, I said cyclic, but if G is regular, then it has relational complexity 2. If G is Sn, it's got relational complexity 2. We'll call all of those things binary, and there's going to turn out to be a smallish number more. Let me talk a bit about the relational complexity of a primitive group. So Churlin conjectured back in 2000 that a finite binary primitive group, relational complexity 2 and primitive, is one of, well, Sn, I just showed you that. CP for P prime, because I've just shown you that a cyclic group has relational complexity 2, and I'm saying that it's primitive, so to be cyclic and primitive, you have to have prime order. An affine group, this just looks like a dihedral group, FP split C2, or another affine group. This is FQ squared with the orthogonal group of minus type acting on it. Just those, he conjectured. Then in 2016, Wiskins and Churlin reduced to the case of proving this for the almost simple groups G, and then just announced, which is why I wanted to have this in my talk, Nick Gill, Martin Liebeck and Pablo Spiga have just proved Churlin's conjecture, which is awesome. Yeah, this is really exciting. So we now know exactly what primitive groups G are the automorphism groups of homogeneous relational structures of arity 2, or type 2 if you want to call it that. They're all known. So then just to finish up, Churlin has considered other primitive groups. So SM or AM are old friends acting on K-sets. We know the relational complexity for that. There's partial results due to Churlin, Martin and Saracino for the other large base primitive groups. It's a bit of a mess because we don't have containment of subgroups gives you bounds on relational complexity, but there's a lemma due to them which says that the relational complexity is no more than the height plus 1. That's why I talked about height a few slides back, and that's why Nick Gill, Pablo Spiga and Bianca Lodeau are looking at the height. So that means that Veronica and I's result now give you for free that if G is primitive and not large base, then the relational complexity is at most 5 log n plus 1. And we're looking to make more precise statements than that, but it's work in progress, so I should stop there. Thank you very much.
Okay, thank you very much. If you want to unmute and clap or do the thing. Great. Well, thanks very much, Colva. Does anybody have any questions?
Yes, question.
Sure, please go ahead. Yeah.
Thank you very much. I really enjoyed your talk. And of course, I'm coming from the graph theoretical side. During your talk, sorry, of course, I joined the talk a little bit late because I was not able to join Zoom because it asked me to use a filter blocker. I don't know why. But if I understand well, I have two questions. My first question is that you can look at the problem from graph theoretical setting. There is a new paper in March 2021 that they introduced this Saxel graph related to the base of a graph.
That's specifically to do with base size 2, yes.
I really enjoyed that one. So yeah, maybe many things that, because I saw that from my graph theoretical point of view, that many concepts you are defining are very familiar to me, but you are looking in group with the lens of group theory. Like this independent set, maybe it is like the independent set in graph or click number, because I'm really interested, but I'm working in algebraic graph theory. Right. So that's one approach maybe, so we can look. And the second one, I think is much nicer, is that there was a talk by Ramin Taklubigash in his Olympiad student was in Princeton and now he's in Chicago. He introduced this minimal representation. Let me, sorry, I write it here. So he introduced, you know that from Cayley theorem, you can embed any graph G in a symmetric group.
You mean any group G in a symmetric group?
Any group G in symmetric group. So yeah, you can generalize your idea to any group. And there is a paper that says the generalized basis of a group, finite group. This is a new paper, 2021. March 2021, generalized the idea from permutation group to any general finite group.
Right, so I've been doing this in the language of permutation.
You can look at that point. So I mean that if you look at that point, you can look at also this this idea of a Ramin Taklubigash from Iran that said that you can embed a graph G using this Cayley graph. Now you are looking for the least number, which is called the degree of a finite group. the least number minimal permutation representation of a graph. Means the minimal D that you can embed group G in SD, symmetric group on D, SD, S of D.
And there's some lovely links between minimal representation
and he also defines something that which is very close to your ideas. His idea is to define this, the idea is the minimal faithful representation.
Yep.
Means that you have a group G.
1989 paper, you'll find a link between the minimal degree of a permutation group and which is exactly what you were talking about, and the base size. And then there's various papers citing that which take it further. And then recently there's been Rebecca Wilder.
Yeah, that's my lovely stuff. So what is the connection? Can you tell me in the connection between your work, your research work, and that faithful representation?
So the easiest place to look is in the paper by Martin Liebeck that I mentioned, where he proves the 9 log n. He gives a lovely link there between the minimal base size and the degree of a faithful permutation representation of a group. I can't reconstruct it right now because I haven't been doing so. I mean, the minimal faithful permutation representation is just the minimal index of a core-free subgroup. So there is an awful lot known about that. Lots of the stuff I'm interested in, I really do want the actions to be faithful. So it's easier to start by just thinking with the permutation groups rather than and think of them as already embedded inside SM. But there are really, really strong links between the stuff you just mentioned. And I recommend looking back at that paper from Martin Liebeck from 1989.
Thank you very much. My last question, sorry, very quickly. I'm really interested in classifying those permutation group with BG equal 2 or
right.
K. Okay, so they defined this Saxel graph based on that.
Yes.
And then I realized that you can define it for BG equal K. You generalize the graph. I just find this idea to simplicial complex.
Sure.
And it is a great idea. We can manage to email. I can email you to look at the simplicial complex, because there are a lot of theory by Richard Stanley and this Stanley-Reisner ring. And over there, you can come to the classification of maybe some good idea. I'm not sure.
Yeah, that sounds great. So we know the groups of base size 6, but we don't know the groups of base size 2, 3, 4, or 5. We know that they
you mean every result on those direction is very important? Yes,
absolutely. That sounds like a really nice idea.
Thank you very much. Sorry for bothering several questions. I really enjoyed, and I will in contact with you in the future. Thank you.
So thanks very much. So are there any other questions?
Hello, thank you so much, and it is very nice to listen to you. I just wanted to ask a quick question, that this permutation group is relatable to the automorphism group, because I am also doing some work with the automorphism group, and I am stuck. I'm afraid to tell you that I am stuck, that I am getting the basis 2 for every case. And I also want to share my work with you. When I apply some automorphism group and I choose some parameters, or you can say that some variants, invariants like the fixing set and other as well, I am getting 2. And is this a relatable? I'm afraid that I'm not explaining well, but I know that you are getting my question. Is this relatable, or anything that having the connection between your work and the automorphism group, if you can guide me?
Well, I mean, automorphism group of what? Sorry. So every automorphism group is a permutation group because it's permuting whatever object you're studying. But are you studying codes or graphs or design?
Yeah, I am studying the automorphism group in graphs. Yeah.
Graphs, right?
Yeah, definitely.
Yes.
Definitely.
So yeah, there's let me think. I'm not actually a graph theorist, but if you so graphs with base size 2 is not something off the top of my head that I know, but Cheryl's blinking.
Yeah, I will share my work with you. Actually, my question is that I am interested. I am doing some work in algebraic graph theory as well. Means that I am imposing some algebra to the graphs, and that's why I am moving towards the groups. And I am choosing the automorphism group. And now there will be some bigger permutation group. And there is your talk. If I
I mean,
understand
the groups of base size 2 are not yet classified. There's a big project on the way to try and classify all of the groups of base size.
Yeah, because you were interested, if I am not wrong, you were interested to find some minimal set, minimal with the minimum size, the more minimum.
Yeah.
And it is very, I was very surprised that when I was getting 2 for all the cases, and it was beautiful because the 2 is a simple number, it is very easy to handle. And I am getting the 2 partitions, means that the 2 bases only. I am having the 2 partitions in every case, almost in every case, or there was n. So that's why it was very interesting that you are having something log, and I also having this work from the last 1 year, and I'm getting 2, and I'm stuck with the 2, and I am actually bored with the 2. So that's why I asked this question.
I would recommend looking at actually a paper that the last questioner just mentioned. So there's a paper just recently by Tim Burness and Michael Judici. It's on something called the Saxel graph, and they're specifically looking at trying to describe the groups of base size 2. And I think there's some nice survey background stuff about what's known and not known about groups of base size 2. So I would take a look in their paper, and you might well find some useful.
Yeah, definitely. And please let me know in the chat if there is any link with these, then please let me know. Thank you.
Yeah, or send something to me and then I'll remember to answer.
Yeah, thank you so much. Looking forward to you. Thank you so much.
Thanks very much. Is there any other anybody else who'd like to ask a question? Don't see any hands up or anything in the chat, so so I think that's it. So I think we've had a lovely talk with that beautiful blend of algebra and computation and model theory. I mean, what more could you want for a combinatorics conference? Actually, very beautiful results. And so thanks very much, Colva. And so I'll close the session now, and we'll resume at 10:30 with the contributed talk session. But yeah, thanks very much again.
Thanks, Simon.